Hi, this is Tim Malloy with video 2-3 on RC circuits. This video should be pretty easy, so we can it shouldn't take us that long. Pretty simple problem. So let's get started. So number 6 says the pair of capacitors in the figure below are fully charged by a 6-volt battery. The battery is disconnected and the switch is then closed. So just dive into the circuit. Okay, we have let's say my pen isn't working. What the heck? Okay, we'll just have to use the color or the pen then, not the pointer. So there's let's say there's a battery here. Everything is all charged, and then we take the battery out. Again, like I said, these are charged. And we take the battery out, and then we connect the circuit. What happens? Charge is gonna we'll call that positive place. Charge is gonna go ahead and flow, and then energy is lost through resistor. Current keeps going, and then eventually all the charge will be dissipated, and and the capacitor will be completely empty. The capacitors will be completely empty. I wrote the circuit down here again, just no real reason, I guess. um, okay, now that we understand the circuit, we understand what the problem is asking. We can dive into the questions. Well, I guess more we understand the circuit. I'll get into the question now. And A asks, after 0.7 milliseconds has elapsed, how much charge remains on the 3 microfarad capacitor? B asks the same question, but for the 2 microfarad capacitor. So, again, we are discharging. So we're going to use those discharge formulas for, the discharge formulas we learned in the final add puzzle video for this unit, and we're going to measure the charge. So I decide to start at C equals Q over V. Capacitance equals charge over voltage. Because I know the capacitance for each, I know since that voltage source was 6 volts, that that's how many volts are going to be packed into the capacitors, and then charge I will find. I guess total charge at a full capacitor, charge of a full capacitor. So here it is for the 3 microfarad one. Here it is for the 2 microfarad one. Again, both capacitors have 6 volts. So then the total charge in this charged capacitor system is 30 microcoulombs. Yes, okay. And again, parallel rule for capacitance. Total equals branch 1 plus branch 2, so on. Okay, so and then I decide to use ratios. So I put 1 over total, 2 over total, so that equal to 1. So then we have no matter how much charge is on these capacitors, or how much total charge, 3/5 goes to our 18. Sorry, just our 3 microfarad capacitor, and then 2/5 goes to our the 2 microfarad, the 2 microfarad capacitor. Okay, cool. So now we just find the total charge and at whatever time, and we can use ratios to cut up that charge into how much is on capacitor 1, how much is on capacitor 2. Okay, so that's pretty much the setup. I know I was talking really fast there, but I should have been able to follow it. It's just a whole lot of ratios and stuff together. Pretty simple stuff. These circuit rules are probably some of the easier ones. I mean, I don't even think RC circuits is even that bad of a topic. I think Kirchhoff's rule is much harder. But anyways, so we have the charge at a certain time equals the total initial charge, and then times e to the negative time over RC over resistance times capacitance. So first start off with total charge. Well, we plug that in there, and we have resistance times capacitance, which is actually equal to time, and then we throw that in there. Well, I guess we throw out this number because we multiplied it out and whatnot. So then the charge at 0.7 milliseconds is 30 microcoulombs, or 30 times 10 to the negative 6 coulombs, times e to the 0.7 milliseconds, because that's our chosen time, and then our time constant of 2.5 milliseconds. So then we have I'll go ahead and write QT in there. Total charge at this time is 22.7 microcoulombs. So then we multiply it by the 2/5 for the smaller capacitor, by 3/5 for the larger capacitor, and we're able to divide that total charge nicely into these two numbers for each capacitor. I think I might have them out of order. Let me double check. Yeah, okay, so the greater one is 13.6, which is part A, and the smaller one is at 9.07. Okay, and then I'll just skip down here so I can show part C. What is the current in the resistor at this time? Pretty simple stuff. There's another equation we know for current in a discharging RC circuit. I believe I got all that right. That's total charge over time constant times e to the negative time over time constant. Go ahead and throw that charge that we know so well in. We already knew RC, so I could really just plug in 2.5 meters per second down here if I was a smarter man, if I was a better man, that's what I would do. And then times e to the negative 7 milliseconds, because again, our chosen time is 0.7 milliseconds over time constant. Multiply it out, negative 0.00907 amps. Cut off that negative sign. I believe that just is to denote how the charge is coming out the other side, or it's leaving the capacitor in the opposite direction it came in. I think I got all that right. And that's equal to 9.07 milliamps. And question asks for the answer milliamps. Okay, so that's about it. I feel like I talked pretty fast in the video, but it is simple anyways. So takeaways, one of the easier problems, I believe. And write down the formula, up in, with the charge and with the current. And figure out what you got to solve for. That's a, good thing, because AP Physics, there could be a lot of complicated problems. So write out what you know, and then go through typical setups and understand what the best approach for a problem is what the best approach for a problem is. And then ratios for the capacitors are very cool and nice. Thank you for the video. Thank you for watching the video.